Hello. In this video, we're going to continue our study of titrations. We're looking at how by adding a given amount of titrant, the pH of your sample changes. Particularly, we're going to be interested today in the discussion of this one point right here in this curve, which we call the equivalence point. As before, we're going to be using a BARF table to calculate amounts. Don't forget that every single time you're adding some titrant, the amounts change because of the reaction between your sample and your titrant, and also the volume of your total system changes. We have to recalculate that every single time if you want to get to the pH of your sample at any of these points. Okay, and the very important part about an acid-base reaction is that at the equivalence point, the number of moles of protons is going to be equal to the number of moles of hydroxide ions. That is the most important statement. This is the take-home message for this video. Always think about in terms of the number of moles of the protons and the hydroxide ions for an aqueous acid-base reaction. This is the actual reaction, so you will be tempted, maybe, to just use the formula of concentration volume 1 equals concentration volume 2, or M1 V1 equals M2 V2, whatever different version you may have in mind. But one thing that I want to tell you is that be very careful whenever you're thinking about this particular equation, because according to this statement that the number of moles should be equal to one another, you always have to check the stoichiometry of your reaction and also the stoichiometry of the protons with respect to the molecule, the acid, and the hydroxide ions with respect to the species that carries that. Okay, doing that, remember that volume times concentration gives you the number of moles. In this case, I'm working with millimoles just for the ease of the calculations, but this is going to be the millimoles of the acid. Now I have to check the stoichiometry of the content of protons with respect to the molecule. 1-to-1 in this case. Amounts are the same, but this is very important. Unit analysis is essential, and if you work out the unit analysis correctly, you're always going to get it right. Do not forget to do that. So that gives you the number of moles of protons that are present in your sample, also to the number of moles of OH minus that I need to add from my titrant. Now you can go from this amounts of hydroxide ions, stoichiometry of hydroxide ions with respect to sodium hydroxide, 1-to-1, and then you can divide by the concentration of your solution of sodium hydroxide. That's going to give you the volume of the sodium hydroxide solution that you're going to need in order to completely neutralize your sample of the acid. Now, some of you may be wondering why, if this is 1-to-1, I do even need to do this calculation if I'm going to get the same number regardless. Well, again, the important part here is that not every single one of these species, whether it's your acid or your base, is going to be monoprotic. Always have to take into account the stoichiometry. And by adding these factors here, you are never going to get it wrong. So if you use this, be aware that this only works if you're working with monoprotic species. I will just suggest to do the unit analysis from the beginning. You're always going to get it right. In titration, the reaction always goes to completion. At the equivalence point, you have the number of moles of the titrant equals to the moles of the analyte. Because they're in stoichiometric amounts, both of them are going to get used up. You don't have any more sample, you don't have any more titrant, they all got consumed. The only thing that you have left is the products. In this case, you have to determine the composition and the amounts from the reaction, and we're going to be using the BARF table for that. Remember again, you have to take into consideration the volume is changing, aside from the fact that the amounts are changing, because you have to recalculate concentrations, and with those you can then find the pH, and we're going to be using a RICE table. First part of the problem, we're going to be using a BARF table for amounts. Then second part of the problem, once we know what the composition is, we can work now with concentrations and the regular RICE table. So let's get into the problem. First, BARF table, remember that it's talking about amounts, the amounts before action, amounts reacted, amounts final. Before action, what action? These two coming together to react and give you products. Before action, this is the number of moles that I have in my sample, and the equivalence point should be equal to the number of moles of the hydroxide ions that I'm adding. Both of them get consumed. They go to 0 at the end of the reaction, and then whatever it's consumed here according to the stoichiometry, it's going to be produced. What I have left is just the conjugate base, you can see it here, of my weak acid, plus water as well. Now, because this is a conjugate base, I will need the Kb for that particular species, and because this conjugate base comes from a weak acid, it's going to affect the pH, different from 7, and since it is a base, it's going to give me a basic pH, and then I can calculate the pH through this relationship. pH plus pOH equals 14. Now let's use, once I know that I have a conjugate base, this is pretty much a weak base type of problem. I recalculate the volume of whatever is left on my flask, and then I can set up my RICE table. Again, weak base plus water, that gives you the conjugate acid plus hydroxide ions. The initial concentration in this table, since we're now talking about concentrations, is going to be the number of moles that you got from your BARF table, divided by the recalculated volume, that gives you concentration, change minus X for reactants plus X for products, and then at equilibrium, initial concentration minus X for the reactant, and X in both cases for each of those products. Then, since we have a conjugate base, we need to calculate the value of Kb. We don't have the value of Kb, but first we can write it down in terms of the equilibrium expression. We know that that equilibrium expression is products over reactants. Now, the numerical value is given by the relationship between Ka times Kb equals Kw, so I can get the value of Kb from there. I know the value of Kw, Ka was given in the problem. I get a numerical value. And in terms of the concentrations, both the conjugate acid and the hydroxide ions are equal to X, so I get this X squared. And then for the initial concentration of my conjugate base, my weak base in this case, is just given here in the denominator. Now, from here, I'm going to get a quadratic equation. And one important thing to remember is that with this quadratic equation, when I solve for X, the value that it's associated to is going to be the concentration of the hydroxide ions. So what I can calculate with that, you can solve this quadratic equation whatever way you want. With that, I can calculate then the pOH. I take one of the roots from the quadratic equation, the one that makes physical sense. In this case, it's going to be the positive root. I take minus log, calculate pOH. Now, the pH of my solution is going to be given by taking this, subtracting this value from 14. Then I end up getting this value of about 8.75. As I was expecting, at the equivalence point, since I have a weak acid plus a strong base, the conjugate base is the only product that I have left at the equivalence point, and because this is a base, the pH will have to be higher than 7, and that's just a quick check that I can do with my calculation. Okay, that's how we calculate the equivalence point pH. If you have any questions, please let me know, and I'll see you in the next video.